Record. Okay, we are recording. And this is Exam 1, Chapter 10, 11 review. Be sure this is okay, so we don't get any ambient noises from the hallway. All right. Okay. Chapter 10 is on phases of matter, pretty much. So we'll just run across that, see what we can come up with. Let's talk about intermolecular forces. That is, forces that hold molecules together in a particular phase, solid and gas. Of course, the forces, the intramolecular, are the forces that hold the molecules together. Right? So those can either be ionic bonds or covalent bonds. The forces that hold molecules together in a phase can involve either the dipole or the absence thereof, and London dispersion. Right? Those two forces. Now, of those two, dipoles are the stronger. Right? Much stronger than London dispersion. Well, London dispersion are always there, but if there is dipole, then the London dispersions don't count much. They might be a fraction of a percent contributing to the forces. So if you have molecules with dipoles, those are the dominant forces that hold things together. Now, we can interact dipoles with ions, of course, right? Because they both represent on a continuum of charge, right? A complete charge would be an ion. A dipole would be something less than a complete charge. It would just be a redistribution of electron density, which causes a slight positive on one side and a slight negative on the other. Okay? So if we have that case where we're looking at dipoles, two things contribute to the overall dipole moment of a molecule. Right? One is the dipole moment of the bonds. Right? And the second factor is molecular geometry. Okay? So what kind of bond would have a significant moment? Where you have differences in electronegativity between two molecules that are, two atoms that are bound together. So, let's see. Chem 1, we did trends, right? On the periodic table? We did, didn't we? Yes. Okay. So, electronegativity of an atom is least down here and greatest up here. Right? Electronegativity increases from lower left to upper right. Or on a period, electronegativity is greater as you go from left to right, and it's greater as you go from bottom to top. Right? So the farther apart two atoms are, the greater their difference in electronegativity, and the greater the dipole moment of the bond. Okay? So if you get far enough apart, Then you have an ionic bond, where the electrons are actually transferred from one atom to the other. Right? In order to have a dipole moment without an ion, they need to be separated, but not too far. So, for instance, let's say we have oxygen. Well, no, that's a special case. Let's say nitrogen. Whatever else is bound over here, because nitrogen can have some more bonds. But if we're focusing on the bond, which way is the dipole moment? Remember how we represent that with an arrow and a plus sign on the tail? Right. So would it be going this way or that way? So this is more electronegative than nitrogen?
Oh, no.
It's the other way.
Yeah.
So the dipole moment is that way for that bond. Okay. So if we have, say, ammonia, if we write, remember how to draw Lewis structures? Can we do that?
We did do that.
Okay. I just want to be sure that we've done it once, so this is the refresher. So if we have ammonia, what's the Lewis structure for ammonia? Well, you need the valence electrons for nitrogen, which would be 1, 2, 3, 4, 5. So we got 5 here. And you got 1 for each hydrogen, which would be 3 times 3 is 3. We have 8. Okay? Then you draw your single bonds to each of your hydrogens. And that's 2, 4, 6. Right? 2 for each bond. So we have 2 more electrons. Right? So hydrogen can't take any more electrons. We move from the outside in. So hydrogen is full, no more electrons. So we have to put those 2 on nitrogen. Okay? So when we draw the structure for this, we use the VSEPR model, and it's 1, 2, 3, 4 electron groups. 4 electron groups means tetrahedron. Right? Remember that? Okay, so here's our nitrogen, and we've got hydrogen in the back, and then we've got 2 out here. Right? So the base of the tetrahedron is like that. Right? That's the base. And then up here is our lone pair. Okay? So based on that, we have, we remove these. So there are bonds, and the bonds are going to be like this, dipole moment, that, like that. And then we're going to have extra pair of electrons up here that add to its electron density. So in addition to these, we have that extra pair. And overall, the dipole moment of this molecule is straight up through the middle toward that lone pair. So ammonia is a polar molecule. And we have, generally speaking, and if we want to balance things out, put a 3 there. And each one of these is a positive, which gives you a general positive in this area and a general negative in that area. So now, when ammonia orients itself in a gas or in a liquid, whatever the case may be, it orients so that positives of one molecule are close to and form form an attachment or a bond, a dipole-dipole bond between this molecule and that molecule. Okay, so that's what holds the molecules together, and the strength of that dipole interaction determines physical constants, like boiling point, melting point, so forth. So that's a case of a dipole-dipole interaction. Now, of course, if you put ammonia in a solution of, well, if you put it in an ionic something or other, you'll get dipole-ion interactions. But here, we're trying to keep it simple. So we've only got one thing. It's not a mixture. It's just ammonia. So the dipole-dipole interaction is for our ammonia. You could do the same thing with water. Right? Water is going to be like this, only it has two lone pairs. So it is a very polar molecule, even more than ammonia. Okay? So based on that, if we compare water and ammonia, and we know that the dipole moment for water is much larger than it is for ammonia, what does that say about physical properties? The boiling point of water should be much, much higher than it is for ammonia. Higher temperature for water than ammonia, because the intermolecular forces are stronger for water than for ammonia, right? Okay. How about vapor pressure? Okay. At the same temperature, which one would have the higher vapor pressure? Right, the one with the weaker forces, because the forces that determine vapor pressure are those that hold the molecule in the liquid phase. And if they're weaker, then you're going to have more of them in the vapor phase, and the pressure's higher. Now for water, we have a dipole-dipole interaction. That's a special kind. It's a hydrogen bonding. It's the strongest of the dipole-dipole interactions are hydrogen bonds. Well, in fact, I think your book includes oxygen, nitrogen, and no, oxygen, fluorine, and sulfur, I believe, are involved in hydrogen bonding. So if this is a highly electronegative atom, and that includes oxygen, fluorine, and sulfur, then you have the potential for hydrogen bonding. But you always have to have hydrogen there. You can have dipoles between any two atoms that are different in electronegativities. But for hydrogen bonding, one of them has to be hydrogen, and the other one has to be a highly electronegative atom, like oxygen, sulfur, fluorine. So we covered both the dipole moment of the bonds and the geometry. If we have something like this, methane, there's a slight dipole here. Not a very large one, but it really doesn't matter, because all the dipoles are pointing in toward hydrogen, and they cancel each other out. So methane is a nonpolar molecule due to its geometry. Now, what if? Chloroform. Now we have this. Chlorine is much more electronegative than carbon, so it's this way. So that gives us a polar molecule. Okay. And that's due to both things. The dipole moment of the bonds, which is, this one's greater than any of those, plus the geometry, because these do not cancel out. Okay, any questions so far? I'm trying to hit the most important concepts. What if, I'm going to try to draw a pretty picture. What if we have this one? Okay. Hydrogen chloride. And that we assume this is a gas. It's not dissolved in water. If you dissolve it in water, it's hydrochloric acid. Right? But if it's free gas, we call it hydrogen chloride. So we have a bunch of these. Right? So let's say which one is going to be negative, which one's going to be positive?
That would be negative.
Negative, This would be positive. Okay. So if we have others around here, they're going to be oriented this way. Should be the same size. So we can form bonds like that. Okay. So can we say that there is an electrostatic interaction? Yeah, that's true. Can we say that the molecules find the best compromise between attraction and repulsion?
Yes.
Yeah, it's kind of a guessing, right? That's true. When these molecules are together, they try to seek the lowest possible energy level. And to do that, they put positives as far away from each other as they can, negatives as far away from each other as they can, and align the positives and negatives. So we're going to have another negative over here, and then this one is going to have maybe a positive associated with it, but not too close to these guys. So they optimize their attraction and repulsion to the lowest energy state. That's true. Do these molecules exhibit ionic bonding? No, not as written. And that's true. The way they're written, that's the way they are. The hydrogen and the chlorine are covalently bound. And yeah, I think that's safe to say. Even though when you put them in water, they completely dissociate. But that's a different interaction between these molecules and water. But in the gaseous phase, this is a covalent bond. And we don't have any ions there. And the picture, of course, that gives it away too. Because we don't have any complete pluses and minuses here and there. How about okay, let's use those concepts. And let's say we have another molecule like that, carbon in the middle. So we would have carbon, sulfur, oxygen, and more than likely it's like that, double bonds. See the resemblance between this and carbon dioxide? If you just put an oxygen there, you got CO2. And CO2 is a linear molecule. So this one is also linear. But there are some lone pairs there. What we want to focus on is the polarity of the bonds. So which one's more electronegative, this one or that? Right. You look at the periodic table. So over on the right, it's more electronegative. It's to the right of carbon here, even though it's a little lower, still to the right. And sulfur might be closer to the electronegativity of carbon, but it's more than likely just a little bit more. So even though this molecule is linear, this polarity is much stronger than that one. So overall, polarity for the molecule is toward the oxygen. So that being said, we can say that, and it would also exhibit this type of interaction. Okay. So out of those statements I gave you, only one of them is wrong. There's just no ions there. Okay. So if you see this table, where we have these elements, the noble gases. And then over here, we have the boiling points in Kelvin. So this one is, and these are actual values. Okay? So you notice, as the atom gets bigger, the boiling point goes up. It takes more energy to boil xenon than it does boil helium. So, what's the best explanation for that? Do we have any ions there? No. You have a krypton and a krypton together. You know, where's the ion? They have equal pull in electrons, so you're not going to have any ions. Do you have any dipoles there? No, no dipoles either, because you don't have a different electronegativity pulling on those electrons. So what's left? London dispersion. That's the only thing left.
Isn't that like almost so weak that it's not notable? Like almost.
It's very weak, yeah. But since there's no ionic attraction, there's no dipole attraction, they're out. They're not even there. So London dispersion is the only explanation for this trend. So what does the trend mean? Well, let's see. Let's do a representation of size. Helium's like that, neon's like that, argon's like that, krypton's like that, and xenon is just a monster. Right? So we're talking about the electron density. I mean, that's size of the atom. So what does that mean? That means as you go up in size, you have probabilistically, you have more places for electron density to be shifted. Instantaneously, but still shifted. Right? So for a very instant, we could have more electron density over here, whereas it'd be more difficult to do that here, and even more difficult as you get smaller. Right? So when you do that, you influence your neighboring xenon atom. So this positive shows up, oh, it attracts electrons over to this side of this xenon atom, and that leaves over there. So for an instant, you have this redistribution of electron density, and it's easier, you have more places for it to happen with a larger atom. So that's why you get more redistribution of electron density in a larger atom than you do as the atoms get smaller. So when you do that, the London dispersion forces are greater for the bigger ones. So that's why the boiling point increases as your atom gets bigger. That's the explanation for why the boiling point increases with atomic mass, because it also translated into atomic size. Okay, let's talk about adhesion versus cohesion. First of all, definitions. What's cohesion? It's self-attraction. Right? So if you have water, pure water, it's the attractive force for water molecules and their neighbors to each other. Adhesion is the attraction of, say, in that case, water for something else, like the container, maybe the glass vessel that it's in. Okay, that's it. That's it. That's simple definition. So, how do we explain that? That's a meniscus. You've got a liquid in here. It doesn't matter what this is. You can still explain it in terms of cohesion adhesion.
The adhesion is greater than cohesion.
Exactly. So A is greater than C for this one. The other possibility is this one.
That would just be the opposite.
Right. C is greater than A. Example here is water in a glass container or glass capillary. This one, mercury in a glass container. Two examples. Not the only ones, but good ones. Okay. Let's see. How are we doing on time? We've got till when? 3:50. Oh, we got lots of time. We'll probably need to take a break after a while. How about alloys? What's an alloy? Well, is an alloy a pure substance? No. So it's a mixture. Now, alloys generally are considered homogeneous mixtures, but in point of fact, they're not always homogeneous. The only way you can get a homogeneous mixture out of an alloy is make it its base. Because whenever you have a gravitational field, as the alloy cools, it's going to pull on some atoms more than others. Right? So if you're alloying, if the atom you're putting into the alloy is heavier than the one that's going in, it's going to try to pull it and settle it down. But in general, we can treat them as homogeneous. And there are techniques that people have used over the centuries to pretty much guarantee that you have a homogeneous mixture as far as possible. Okay, so when we talk about alloys, is this a true statement about steel? Okay. Carbon fits in the holes of the iron crystal. Is that true? Now we're talking about what type of alloy is it? Is it a substitutional? Oops. Or is it a interstitial? Okay. What type is steel actually? And then we'll look at the statement to see if it's true. Is steel this kind or that kind?
Say interstitial.
Yep. So this statement is true. Carbon fits in the holes of the iron crystal. So that's true. Okay, the presence of carbon, actually the carbon-iron bonds, because they do bond as you fit the carbon into the crystal structure, you did get carbon-iron bonding, yields harder, stronger. Stronger than pure iron. Is that true?
Yes.
Yeah. What it tends to do is it locks these crystals in place so they can't be shifted. Pure iron is a very soft metal. I mean, you can scratch it with your fingernail. But once you put carbon in there, you can make nail files out of it. Okay? Okay, that's true. How about, well, I already gave you this one. Pure iron is soft, ductile. That just means it can be bent and pulled, stretched. Why? Because it lacks directional bonding. What does that mean? Directional bonding is like the electron density in the bond is on this axis with the next atom, and it stays there. Those electrons do not move. Is that true for iron? Remember the theories about metallic bonding. Okay. This goes back to, well, an earlier version was known as the, what is it called? The electron sea, where you just have iron nuclei floating in a sea of electrons. Right? But that didn't explain it. So that was out. So we had to go back to molecular orbitals. So if you have two iron atoms together, right, they have their valence electrons here, and then they have their molecular orbitals. But as you start increasing the number of iron atoms, remember molecular orbitals are spread over the entire lump of whatever it is. So once you get up into the neighborhood of a mole of iron atoms, you have almost a continuum of molecular orbitals available. And the highest energy of those is that are occupied with electrons are at such low, the difference in energy between this one and the next one is such low, it can jump, right? So what that means is those electrons can move in any direction. They're non-directional, right? So this characteristic is soft and ductile because when you push on the nucleus, there's not much there to hold it because those electrons can, all right, I don't want to be here if you're going to push on me. I'll just jump over here to this other guy. So they lack directional bonding, right? That's true. Make a long story short. Let's see, where was I? Oh, here we go. Okay, and the last one, the amount, or actually the percentage carbon in the alloy significantly affects properties of steel. I kind of digress. So we're talking about steel. So if we, well, with the exception of this one, but as you add carbon to it, the more carbon you add, there are significant changes in the properties of steel. Right? The more of these holes you fill up, the more it affects the properties of the steel. Right? If you get to, let's see, 2% or greater, that's known as high carbon steel. That steel can hold a very sharp edge, but it doesn't hold up well to bending. Right? It's not strong. It's not. There's another word for that.
It's not very valuable.
It's on the tip of my tongue. It's not strong. It's
brittle. Brittle?
Yeah, it's the opposite of brittle. When you get up to above 2%, you end up with brittle steel. It can hold a very sharp edge because those crystals are locked in place. But if you try to sword fight with it, and the other guy has a lower carbon steel, he can just snap your blade in half. So hopefully I'll think of it. There's a term that they use for it. So the amount of carbon does affect properties of the steel alloy. Low carbon steel is around 0.5% carbon. So it doesn't take much. So what everybody knows the katana, right? Japanese sword. The solution that the sword makers in Japan came up with was they had low carbon steel and high carbon steel. And in the process of making the sword, they embedded the low carbon steel in the center of the sword, in the body of the sword, and then the outside layer was the high carbon steel. They bonded them together so that the inner low carbon steel gave strength to the blade so that it wouldn't break, but the outer was the edge, the really hard steel that would take an edge to keep it in. That was their solution to the problem. Durability? Durability, I think, is the word I'm looking for. The low carbon steel is more durable. It can stand up to punishment, up to a limit.
So let me ask you a question. How does quenching hot steel like boiling water strength?
Yeah, okay. Hot quenching. So this is the way I've seen it explained. You have this lattice of iron atoms. And then you have some in the back and so forth. But as you heat it, the carbon is already in there, right? And as you heat it, that drives the bonds apart, just slightly, so that carbon can get in the middle, right? And then if you quench it quickly, that's not enough time for the carbon to leave those spots. So it recontracts and they're stuck. Now, quick quenching, that depends on what you're trying to make. Quick quenching does that for steel. But sometimes when you do that, when you cool something, quick quench it, you create stress lines of stress in the body. So in order to relieve those lines of stress, you anneal it. Put it in an oven, heat it up, let it cool down slowly. That wouldn't work for this because it defeats the purpose. But for some things like glass sculptures, right? Once you make those and you've added all this glass to your sculpture, you've got this little unicorn that you've made out of glass, molten glass. If you leave it like it is, you could have it sitting on your shelf by the door, and in the winter, it gets real cold outside, you open the door, blast of air comes in, it goes, it shatters because it has lines of stress in it. So you take that glass thing, stick it in an oven, heat it up to a certain temperature, and you gradually cool it, and that relieves those stress lines. And then it's more durable. Okay. So let me see, move on here. How about, let's define, let's say we have a solid crystal of sodium chloride. We've made a brick of rock salt. Something like that. Sodium chloride comes in cubes anyway. So at least as far as the cube goes, it's accurate. It's a cube. Okay, so what are characteristics of this ionic solid? Well, let's talk about its hardness. Is it soft or hard? Mm-hmm. Ionic solids are notoriously hard. How about melting point? So it's high melting point or low melting point? High melting point, right. The attraction of ions to one another is a force that takes a lot of energy to overcome. How about electrical conductivity? Is it low or high? If you put an electrode on this side, electrode on that side, say this one's positive, this one's negative, are you going to get a current through that? That's right. No, you're right. No. Why? Well, you have ions in here, that's true, right? Yeah, positive and negative ions. But what has to happen for a current to flow through anything? Those ions have to be mobile. If they don't move, you don't get a current, right? In a ionic crystal, those ions will not move, right? So you don't get a current in solid. So low electrical conductivity. What do you need to do to get those ions to move? Right? Melt it, then you can get a current through it. The other possibility is, if it's soluble, dissolve in water. Then you separate the ions and they can move freely. But if we're just talking about that, about the solid sodium chloride, it won't conduct electricity unless you melt it and turn the ions loose. Okay. Erasing searchers. Hello. Oh, good. It's recording. For a minute, I thought I forgot to start it. So, review is recording, so you can look at it later.
All right.
Let's see, next Monday is Labor Day, right?
Yeah.
Right. So we skip that one, and then the Monday after that, we come back for an exam.
So 2 weeks from today.
Right. Are you having any luck signing into Cengage?
I haven't got it yet,
Oh, okay.
but I didn't have a hard time last when I got it last semester. You know,
Okay.
so I should be able to get onto it easily.
Let's see. Well, let's see, I don't want to beat this horse too much, but let's compare that one with that one. Okay? So we know this one's sodium chloride. What's this one?
Carbon chloride?
Carbon tetrachloride. Okay. You've already forgotten type 1, type 2, and type 3 naming convention, right? Two nonmetals together. You just name them and say how many there are. So carbon tetrachloride. Okay, so the question is, which one has the higher, let's see, which one has the higher melting point? Think about what forces are being overcome. To overcome the forces here, you're having to break ion-ion attractions, which are very strong. So this one has a very high melting point. What forces are overcome here? Well, the covalent bonds between these atoms are much too strong to overcome, unless you go to monstrously high temperatures. But by that time, you've melted it. Right. So if this carbon tetrachloride is solid, it's going to happen at an extremely low temperature, right? Because this molecule is a symmetrical tetrahedron, and even though the bonds are polar, it's symmetrical, so they all cancel out. So the molecule itself is nonpolar. That means it has a very low melting point. Right. So the attractions between individual carbon tetrachloride molecules are due primarily to London dispersion force, because we don't have any dipoles there. Well, theoretically, you still have little dipoles here, but what are they going to attract to? Right? Because the positive is here. It's buried, it's surrounded by these guys. So the negatives can't get to it. Right? So for all intents and purposes, it's nonpolar. Okay, let's see if there were other questions here.
Is a copy of that review on Blackboard?
Yes, right. It's still in Blackboard. And it's got a fillable form, it's got the key, and it's got how I did it.
Okay. And then the homework on stage isn't due until the day of the test, right?
Right.
Okay.
You got lots of time. And I was telling this pair here earlier that I'm not going to record the grade from the homework until the day of the test, because you may work on it a little bit, go away, and come back.
Okay.
So I don't want to put an intermediate grade. I'm just going to wait
So
till.
you're just going to grade the homework when you grade our test?
Right. Actually, Cengage grades it for me.
Okay.
So I'm gonna wait and collect the grades on the day of the test. Let's see. Well, that's enough said about that. Let's see. We can talk about phases. without looking at the phase diagram, let's say we have normal atmospheric pressure. So that would be 1 atmosphere. And we're talking about water. And we set the temperature at 0 degrees centigrade. So at that pressure and that temperature, what phases of water can exist at the same time? Can there be more than one at the same time? Right. This is what? Freezing point of water? So what phase of water can exist at that temperature and pressure? This can exist. Not does it. Can exist. Can the solid exist? It's at the freezing point, right? Right, so we could have a solid there. How about the liquid? Can the liquid exist? It had to be one or the other, right? Right. You can have both liquid and solid at that temperature and pressure, right? Remember let's see, as we increase, let's see, what are we going to do? Temperature. As the temperature increases, and this is the progress, whatever. So if we start off at a solid here at very low temperature, so that's 0 degrees, okay. And say this is -40 degrees. We start off here at -40 degrees, the only thing you can have is solid. Once you get up to the melting point, temperature flattens out. It stays there until all the solid is gone. Then once all the solid is gone, it starts going up again. And here it goes up to 100 degrees. That's not to scale. It's close, but not exact. So at this point, you have, down here you have solid only. Here you have solid and liquid. And here you have liquid only, increasing in temperature from 0 to 100. Once you get to 100, the boiling point flattens out again. And you have liquid gas. Until all the liquid's gone, then the gas can be heated again. So what's going on? Well, when you're on this curve, the energy that you're adding is heat. It's just adding to the vibration of the molecules. You're making them move faster. But when you get to this point, the energy you're adding is actually breaking the bonds between the solid in that crystal that's been vibrating. You're breaking the bonds so they can move past one. Right? So until you finish breaking all those bonds in the solid, then it stays there. And then once all those bonds are broken, you've got a liquid. Now you're vibrating again. So you've got these liquid water molecules moving around. And you keep heating them up, and you're adding kinetic energy to those water atoms, molecules, until you get to this point. And now you're at the point where the energy you're adding is causing the bonds to break completely between the liquid molecules, and they're going into the gas phase. So from here to here, you're breaking the intermolecular bonds between the liquid molecules and making gas out of them. Once you've broken all those bonds and you're in a gas, then the energy you add is, well, since it's a gas, you're just adding kinetic energy to the gas molecules. They're flying around. Okay? Let's see, definitions. Let's draw a phase diagram for something. We can make it water. So what does a phase diagram look like? Well, let's see, pressure is here, and temperature there, I think. Wait a minute. That's the other way around, isn't it? Hold on a second. Yeah, temperature's here, pressure's there. Okay. So, generally speaking, the solid is going to be in this zone, the liquid's going to be in this zone, and gas is going to be in this. So what we do is we have, as the pressure increases and the temperature increases, like that, and then from here, let's go up a little bit more. For water, for most substances, the phase boundary between solid and liquid is positive slope, but for water, it's negative. So it goes like that. Okay? And then between phase boundary between liquid and gas, like this. Okay? Now, what do these lines mean? Well, the lines mean that for this temperature and pressure, at that temperature and pressure, you have solid and gas at the same time. For this line, at that temperature and pressure, you have liquid and gas at the same time. And for this line, you have solid and liquid at the same time for those different pressures and temperature combinations. Then there's some points. At this point, which is the triple point, you have solid, liquid, and gas all at the same time. And that only happens at one combination of pressure and temperature. And then what's this one? That's the critical point. Beyond this point, there's no division between liquid and gas. It's just fluid. You can't tell whether it's liquid or gas. Beyond that temperature, beyond that pressure, so it's usually very high pressure, very high temperature. You're in the supercritical region. Okay? So I was going somewhere with that. Let me see. Oh, okay. So if we're going through a phase change, let's say we hold the pressure constant here, and we increase the temperature. We cross that line. So when we go from solid to gas, what do we call that? It's got a name, right? If you go this direction, it's called sublimation. If you go from solid to liquid, say we hold the pressure constant, and we go like this, right? From solid to liquid, that's just called melting, right? If we start with liquid, say at this pressure, and we go from liquid to gas, that's called vaporization. You can call it boiling too, but it's vaporization. Now you can go back the other direction too. Melting, the opposite of melting is fusion. The opposite of vaporization is condensation. What's the opposite of sublimation? Starts with a D. Deposition. Okay. So those are the 6 possible transitions that can be made in a phase change. Let me see here. Let's remove some of this mess so I can use the diagram again. Yes. Okay. We're going to change this one to a conventional positive slope. So we're not water anymore. Okay. Let's see. All right, so this is not water. What happens to the, let's say this is 1 atmosphere. That's the 1 atmosphere line. So can we say that the melting point of the solid increases with increasing pressure? So what's the melting point? Where's the melting point at 1 atmosphere, say? Right there. Right there, melting point at that pressure. What if we increase the pressure? Where's the melting point now? So did the melting point increase with pressure? Yeah. Right. Temperature increased as we increase pressure. That's characteristic of a positive slope. Okay, let's see. Definition. What's the measure of resistance of flow of a liquid? There's a word for it. What describes the resistance to flow of a liquid? Viscosity. The more viscous a liquid, the slower it flows. Molasses in winter, right? Or if you have butter, take it out and put it in the frying pan, heat it up, right? It doesn't flow very well as a solid, but you heat it up, it makes a liquid, it flows pretty good. It spreads all over your pan. Okay. Oh, there is more. Let's see. How are we doing on time? All right, one last one for this group. Let's say we have these compounds. And this is a partial representation of their structure as well. Now the convention is, when I write these hydrogens next to that carbon, they're not bound to this molecule, this atom. Right? They're bound to the carbon. And the carbon is bound to that atom. Okay? So it would look like this. And those would be your hydrogens. Okay? That's the convention. So when I write these here, these carbons are bound together and the hydrogens are sticking off the carbons. Okay? You would be tested on that until you get to organic chemistry. Let's see. 1, 2, 3, 4. Okay. And 1, 2, 3. And then this one. There we go. Okay. So the question is, which one of these has the highest boiling point? Well, process of elimination. Let's get rid of the ones that are non-polar, right? How about this one? Is that polar or non-polar? Even though it's got an oxygen there, and it's going to be like this and like that, it's still non-polar because they cancel each other out. Right? So that one's non-polar. Where are the other non-polars? Do we have any more? All of these are non-polar. All those bonds between carbon and hydrogen are slightly polar, but they're symmetrical in the tetrahedron around each one. So they cancel each other out. These are non-polar. There. So the only two polar molecules are this one and that one. So we have polar and polar. Now we have to decide, if we're going to say which one is the highest melting point, we have to say which one is more polar. All right? So you can have a dipole-dipole interaction, but which is the strongest of the dipoles? Hydrogen bonding. Right? So which one has hydrogen bonding ability? That one. Chloroform is polar, but it's not as polar as ethanol. So this one has the highest melting point because of the hydrogen bonding. Polar, but at the upper end of polar. All right, let's see. Mm, 3:50. So I've got about an hour and a half, or hour and 25 minutes for chapter 11. I think any of those that I've made, I guess I would use those. Let me verify it. So when you look at the review document for Chapter 10 and Chapter 11 for that matter, these happen to have easy, moderate, difficult subdivisions. The difficult ones, you won't see those except on bonuses. So if you want to get practice working on those for a potential solution of a bonus problem, then that's the place to look, the difficult ones. Now, if we have time, I'll come back to them. But let's get our Chapter 11 review out of the way. And if we have time, we'll come back. So now we're going to talk about Chapter 11. This is particularly focused on solutions. So, expression of concentration of solutions. Why don't you take this one? So, if we start off with a 0.1 molar sodium chloride aqueous solution, okay, that's our starting point. Which one of the following will be closest to that actual value? If we express this in mole fraction, or if we express it in mass, well, this is mass fraction. Mass fraction is like percent, only divide by 100. Right, take the percent part out of it. That's all mass fraction means. Or if we say mass percent, or if we say molality. Okay. The units of measure of mole fraction, this is dimensionless, right? It's just a fraction. It's a number, right? Because you got number of moles of sodium chloride divided by the number of moles of the solution. Okay? Mass fraction, well, let's take mass percent first. This is parts per 100, like mass of sodium chloride per 100 grams of solution. Okay? What's molality? It's moles per kilogram of solid. Okay? And this is mass percent divided by 100. Just take that one, divide by 100, and you get mass fraction. So, we can calculate those out, find out what's the value for each one. If this is 0.1 molar, we can say, all right, if that's 0.1 molar, that means moles of sodium chloride per liter of solution, which is water and sodium chloride, moles of solution. But if you're taking a test, you want to do this quick, right? You want to get it out of the way. So logically speaking, which one would you think, let's use some intuition. Which one would you think would be closest to this one in absolute value, in the size of the number? Well, the one whose units are closest to the units here, right? So which ones have units that are closest to those unit representations, moles of sodium chloride per kilogram of solid, right? How much for 0.1 molar, that's a fairly dilute solution. It's dilute enough so that a liter of solution is very close to a kilogram of solid because this is water. And the density of water is 1 gram per milliliter, or times 1,000, 1 kilogram per liter. So if a liter weighs a kilogram, then a liter here would be approximately a kilogram there. And this doesn't change from there to there. So this one would be very close to 0.1 molar. It's actually just slightly larger. I did the calculation, and it's 0.1006 mol is 0.1 molar. Okay? Otherwise, you've got to do the calculation for each one, which I did in the worked problems. Right? If you want to take a closer look at it, then it's there. Okay. Let's see what else we can say about solutions. How about this one? Which ones of these respond to temperature change? See, we've got mass percent, right, which is mass. Right? So the mass of the solute divided by the mass of the solution. Mole fraction, molality, molarity. Right? Which ones of these respond to changes in temperature? When we change the temperature, do either one of these masses change? No. No, mass is a constant, no matter what the temperature is. So that one doesn't change. How about mole fraction? That's numbers of molecules. Do the numbers of molecules change as you change the temperature?
No.
No. How about molality? That's moles per kilogram. Right? We just said numbers don't change, moles. We also said that mass doesn't change, kilograms. Right? So this one doesn't change either. How about this one? Molarity. This one is moles per liter. Does that one change with temperature?
Yes.
Because the volume will expand, giving you a lower molality at higher temperatures. So this is the one that changes with temperature. Now, it has to be, for aqueous solutions, it has to be a pretty big change in temperature. Or you have to be interested in extreme precision, accuracy, I should say, extreme accuracy to several decimal places to see a difference with only a few degrees change. Okay, which one of these is an endothermic process? Evaporation of water. Is that endothermic? Okay, when water evaporates, it goes from liquid to gas. How does it do that? It has to break bonds, doesn't it? If it breaks bonds, it needs energy. So energy has to go into it. It is endothermic. Okay? How about the combustion of gasoline? Say, burn gasoline. that endothermic or exothermic? Right. It gives off energy. So this is endothermic. Yep. That one is exothermic. Mixing of sulfuric acid and water. I don't know if you'll know this one or not. Sulfuric acid and water. Is that exothermic or endothermic? Yes. If you mix acid and water, it's like the rule, do as you oughta, add acid to water. That's because it's exothermic. If you added water to acid, the release of energy would be sufficient to boil the water, and it would splatter in your face. So we add acid to water because with a large amount of water, you're making a very dilute solution to start with, and the heat is dissipated throughout the mass of the water, and then you can bring it up gradually. So this is exothermic. Freezing of water. So you're going from liquid water to solid water. So what's happening? You're forming bonds here, locking it into a crystal structure. Which one is at the lower energy state? The solid. So if the solid is lower energy than the liquid, it has to give up energy somewhere. And as water freezes, it gives up energy. It's exothermic. So this is the only endothermic of those four. Let's see here. Okay. Let's see, this is Henry's law. So if we have a container with a movable piston in it, and we have some solution here, let's just call it water. And we have a gas up here that's not water. It could be water, but it doesn't have to be. So what's going to happen if we apply a force to that piston and the piston is driven down? Okay? What happens is the pressure of the gas initially increases, right? And the amount of gas in the water also increases. So as we put pressure on that gas, that drives the gas molecules closer together, which means they're more concentrated at the surface, which means they're being pushed into the water. And since the concentration of gas goes up as you decrease the volume, there's not enough space out here for that much gas. So it has to go into the water. Okay. How about temperature? This is just general relationship between vapor pressure of a gas dissolved in a liquid. As the temperature changes. let's say the temperature goes up. What happens to the vapor pressure of the gas over the liquid? Does the gas go into the water or out of the water, the liquid? Into the liquid or out of the liquid? In most cases. It goes out. Right? As you increase the temperature of the liquid, that increases the kinetic energy of all the molecules, liquid and gas. And that causes the dissolved gas to leave the surface of the liquid with higher frequency. So it puts more of that gas into the vapor phase because it has higher energy. Right? Less of it is returning, more is leaving at higher temperature. So that means the solubility of gas in liquid increases as temperature decreases. It's counterintuitive. But if you explain it that way, it makes sense. Because as the temperature decreases, the kinetic energy of the gas in the headspace is decreasing. And the lower energy state is found in the solution rather than as the gas. You can describe it either way, either increasing temperature or decreasing temperature. But if you describe it as increasing temperature, then the converse has to be true as well. So, I think I said it before, that's why I take my bottles of pop and get them cold before I open them. Because more of the CO2 is dissolved in the liquid at a lower temperature. And you can tell, all you have to do is just crack one open that's at room temperature versus one that you've had in the refrigerator, and you can audibly tell the difference between the pop. That's why I hate going to picnics. Because they always have the 2-liter bottles at 100 degrees, right? And you open it up and go, whoosh, there goes your carbonation, you know. Unless you're the first one to the bottle, you know. But pretty soon, carbonation is gone. And you're just drinking flat Coke or flat whatever. Okay. Let's see. Let me try this one. Let's see. Yeah. Okay. Here's the scenario. This is what's given. So if the this liquid contains 1 mole of A as a liquid and 3 moles of B. So the ratio here is 1/4 A and 3/4 B. Okay. The vapor pressure here above the solution, which this has to be closed in order for that to work, is 314 torr. And this is all at 25 degrees. Right? Temperature doesn't change. Okay, that's the situation. The extra information we're given is if we have pure A, okay, pure A, the vapor pressure is going to be 265 torr. And if we have pure B, the vapor pressure is 355. Okay? This is the mixture, solution if you will, and these are the pure liquids. Okay. Let's see. Make sure I'm on the right track. Okay, I didn't work it right here. So I better work it right. So if that's pure A and that's pure B, then, and this one is due to 1/4 A and 3/4 B, then the contribution to this total should be 1/4 of A, right? So we have 1/4 of A is contribution and 3/4 of B, right? Let me see what that is. $265. So this is 66.25 for contribution from A, and the contribution from B is 266.25 torr. I'm going to have to round those off later anyway. So we would expect this contribution and that contribution to add up to give you that value. So what is that total? 332.5. So round it off, 333. That's what we would expect if these were ideal liquids, if they did not deviate from Rayo's law. So 333 is expected. But what do we get? We only get 314. So what's the deviation from Rayo's law? Positive or negative? Negative, right? It's less than we expect. So the deviation is negative. So what does a negative deviation mean? In terms of interaction of A and B. What it means is A interacts with itself a certain way, and B interacts with itself a certain way. That's why you get these values. But when you put A and B together, there's a stronger interaction between A and B than either A with itself or B with itself. Because the stronger interaction keeps A and B in the liquid phase, not in the vapor phase, right? So stronger interaction of the mixture means lower vapor pressure. How would that look on a diagram? So this is fraction of A or B. So let's say B is the higher pressure, so it's going to be steeper. That's B. This is 100% B. And this one, like that, this would be 100% A. Right? So this would be 355. If these were pure, and this would be 265. Right? But when you mix them together with A at the lower concentration, so A would be down here, B would be here, we would expect an additive. But we get, instead of this one, like that, which would be ideal, no interaction, we actually get that. That's a negative deviation. Okay? would positive deviation look like? Flip that up. Right? Positive deviation would give you a higher value here than you expected here. So say if this expected was this, this might be 360 or 370. Okay? Now this is the case where two volatile liquids are put together. If you have a non-volatile solute in a volatile solvent, then the calculation is very simple. The actual pressure is equal to the mole fraction of the solvent times its pure pressure, right? So if A were non-volatile, and we had 3B and 1A, then we would expect our vapor pressure to be 266. Because the non-volatile A wouldn't contribute to the pressure at all. Does that make sense? Okay. When you have two non-volatiles, you have to splice those together. And that's not even considering azeotropes. Did your book talk about azeotropes? And okay, an azeotrope is when you get two volatile liquids together and you start heating them up, you reach a point where their individual boiling points reach a crossing point, and then the boiling point stabilizes where a mixture of the two comes off. Right? And at that point, that's as high as the concentration you can get. Can't get any higher in concentration. Say you're trying to distill booze. Okay? So you got ethanol, that's my abbreviation for ethanol, and water. Right? So you can start off, and of course you're going to have methanol in there too, in your mash. So this one boils at a lower temperature, so when you start boiling it, methanol comes off first, and that's the fraction you throw away, because you don't want to kill your customers. But then the ethanol starts coming off. And when you reach a concentration of 95% or thereabouts ethanol, the ethanol and the water form an azeotrope that boils at a certain temperature, and you can't separate the two by distillation. That's an azeotrope. So how do you get absolute alcohol, crystal clear? Well, two possibilities. The laboratory way, on a small scale, is you use some sort of solid, usually a salt, that will absorb the water. So you just filter it through that, like sodium sulfate, anhydrous sodium sulfate, and it absorbs the water, and you've got your pure ethanol. Right? But that's not effective for large-scale production. So what you do is you add a little benzene. And that forms a three-part azeotrope. And what it does is it allows this, this, and this to come off, so you lose some of that, but you get rid of all of that. And what's left behind is 100% pure, 200 proof ethanol. I don't know if they let you do that anymore since benzene is considered a carcinogen. That's the way you used to do it. They might use something different now. Okay. So let's see what else we got here. How about osmotic pressure? So if we stick a cucumber, got a slice of cucumber, and we put it in, a solution that is, let's say it's saturated sodium chloride solution. What's going to happen to that cucumber? Is it going to get crispy or limp? It'll get limp. Why? Because the cells in here have more water in each cell than the water out here. The concentration inside the cell is higher in water than outside the cell, and the water is going to move across that cell membrane to try to equalize the concentration. Right? So the water moves out of the cell, and the cells get limp. The concentration of salt, or dissolved solids, we might say, inside the cell is increasing as the water leaves. So if the amount of solution out here is not large enough, and the piece of cucumber is big enough, you may eventually reach an equilibrium where the concentration outside is the same as inside. It'd be hard to do, but possible. So what do we call this solution relative to the cucumber? Is it isotonic, hypotonic, or hypertonic? This solution, one of these, well, it can't be isotonic because we got a limp cucumber to show for it, right? It's not the same concentration inside and out. If that were true, water wouldn't move at all. So it's got to be one of these. So is this solution hypertonic or hypotonic? You have 50-50 chance. It's hypertonic. The hypertonic solution has a tendency to transfer water into itself. Let's put it that way. So hypertonic solution, in a medical sense, is something you don't want to give to the patient. Except for very special conditions, right, where they need a hypertonic solution. And you don't give them a lot either. You know, if they're short on, say, if they're hypokalemic or potassium, they're very low potassium, then you might give them an injection of a hypertonic potassium solution. Not much, because you can stop their heart if you give them too much. Hypotonic would be like distilled water. And that would mean that the water would move into the cucumber and it would swell and get crispy. Okay, how are we doing on time? We're good. If you need to, do you need to take a break? Or you want to finish this? Yeah, if you have to go, go. Let's see. Okay. What does osmotic pressure depend upon? Since we're on that subject, osmotic pressure, right? Or abbreviated pi, right? Does it depend upon atmospheric pressure? Does it depend on molarity of the solution? Does it depend upon temperature? Or does it depend on, oh, which one does it not depend upon? That's the way this question is. Not depend. Okay. Or the ratio moles of solute to solution volume. Well, let's be real here. Those are equal, right? Molarity and ratio of moles to solute to solution volume is the same as molarity. Right? So we really only have to consider these three. Right? What is osmotic pressure dependent upon? Oh, not dependent upon, excuse me. What does it not depend upon? Does it depend upon molarity? Yeah. Concentration of the solute, definitely. So it depends on this one and that one. How about temperature? Does molarity change? I mean, does osmotic pressure change with temperature?
Yes.
Yes, it does. So, by process of elimination, we would either say, if this one were not part of the dependency, then we would say none of them. But as a matter of fact, osmotic pressure does not depend on atmospheric pressure. So you should get the same osmotic pressure from a solution on the shores of the Dead Sea as you would at the top of Mount Everest. It only depends on that difference in solutions across that membrane. Okay, let's see here. Okay. This is going to segue into our lab. So let's say we determine the molar mass of a solid by freezing point depression. So we're going to use that relationship where the difference in freezing point temperature, right, is equal to what? Molality is a factor, right? And the freezing point constant is a factor. What other factor could we possibly have? Right? Yeah, what do we call that? So that's, I'll probably think of it right before I find it. Van Hoff factor. Okay. Van Hoff factor is I. What does the Van Hoff factor depend upon? It depends upon dissociation of the solute. Right? If the solute does not dissociate at all, then the Van Hoff factor is 1. Right? Because then the concentration that you think you have is the actual concentration you have in solution. But if the solute does dissociate, such as sodium chloride, right? So in solution, sodium chloride dissociates into sodium ions. chlorine ions. So the theoretical I value for this one would be 2. Because you think you have this concentration there, but you actually have that and that concentration. So you'd have that one there, and you would actually have 2 times the concentration you thought you had. Okay. So now, let's say we determine the molar mass of a solid by freezing point compression, and we know what the true value is. So the molar mass, or abbreviated molecular weight, true value, the one we determined experimental is greater than that one. But in this particular problem, it's 10% greater. Right? So what does that mean? Well, what could possibly be the reason? Well, I've sort of given you the answer here. If this compound does not dissociate, then we should get a molecular weight that's very close to the true weight. But if it does dissociate, then it's giving us an increased molality, or moles per kilogram. So it's saying that this is greater than it really is. Because if we knew this value, then the factor that's over here would be pulled out over here, and the true value would give us that one, not this one. But say we don't know that. We don't know that it dissociates. So this factor, which might be 1.1, right, just a small amount, 10%, 1.1, is here. But instead, we don't know it's there, so we calculate it as part of this value up here. And that means it has to come from that one. So that's where you get the 10% increase in moles that you thought you had, but really don't have. Does that make sense? The error is higher than it should be. Because we didn't know that it dissociated. It doesn't have to dissociate much. Just 10%. Let's see. Okay. Let's compare 0.1 molal of sodium chloride uh, 0.15 molal glucose and 0.1 molal calcium chloride. Okay. Which one would have the highest vapor pressure? Remember, the vapor pressure is higher if the solute is at a lower concentration, because as you increase the concentration of your solute, you decrease the vapor pressure of that liquid. Right? So for the highest vapor pressure will be due to the one that has the lowest concentration. Now, which one is actually the lowest concentration? Well, what's the concentration here of ions? 0.3 molal. Right? This one doesn't dissociate, so that concentration is valid. How about this one? That one is 0.2 molal ion. So the vapor pressure is going to be highest for that one. Glucose will give you the highest vapor pressure for that one. Which one has the lowest boiling point? lowest boiling point. The lowest boiling point so how do we affect the boiling point by adding a solute? The more you add, the higher the boiling point, right? It's freezing point depression, boiling point elevation as you increase the amount of solute. So with the boiling point, the higher concentration will give you the highest boiling point. The lowest concentration will give you the lowest boiling point. Glucose again. That is the lowest concentration. Okay? Yes, no, maybe? Good, okay. Let's see. And that's just the converse. Let's see what we got over here. Okay. We got time to do at least one of these. All right. See if I can twist your heads around backwards. Given the vapor pressure of water at 25 degrees is equal to 23.8 torr. Okay? The molar mass of glucose, excuse me, molar mass of glucose is equal to 180 grams. Oh, that's given. The mass of the solvent that's mass, not molality, sorry, is 500 grams. And the solvent is water. Okay. This is the beginning vapor pressure. We want the final vapor pressure to be equal to 22.8 torr. Okay? So, if this is pure water at that temperature, and this is going to be at the same temperature, right? So we can use Rayo's law here. And this says that the mole fraction of water times this one, which is pure water, will give us that. So we know what this one is, which is 23.8 torr. Right? We know what this one is. What we need to know is what's the mole fraction of water to solve that problem. Okay? So we can solve that. The mole fraction of water is equal to 22.8 divided by 23.8. See if that's right. 22.8. that should be, let me check this out. That is 0.957983 mole fraction. I want to use a bunch of decimals just so I can minimize the error. Okay, so this is the mole fraction of water, which means we need to know the moles of water per moles of solution. That's what that means. So we need to know okay, we can set this equal. So what are the moles of, what does this expression mean? This expression means that we have moles of water divided by moles of water plus moles of glucose. Right? That's what that's equal to right there. So, if we know how many moles of water we've got, we can solve for how many moles of glucose we need. Right? So how many moles of water do we have? We got 500 grams. Can we convert that to moles? Sure. So how much does 1 mole of water weigh? 2 hydrogens, 1 oxygen, 18.02. Right? Because that's 16, rounded off, and this is 1.01 times 2, 2.02, 16. Okay, so if we divide 500 by 18.02, we get 27.75 moles of water. So now we can put that in this formula. 0.95793 is equal to 27.75 divided by 27.75 plus, we just call that X, which is moles of glucose. So now if we solve that, we have to multiply this expression times that, so 27.75 times 0.9578, 95793. Is 26.58. 26.58, these two, and then plus 0.9573x equals 27.5. Okay? So now we keep this x on that side, and we subtract this one from both sides. So 2775 minus 2658. Is 1.17. So now we have 957, oops, let's try that again. 0.95793x equals 1.17. Okay. Now to find out the moles of glucose, we just divide that one by this one. 1.22 moles of glucose. Right? But the question was, what's the mass of glucose we need? Right, so we just say 1.22 moles. We need to convert that by canceling moles and leaving the mass. Here's our conversion factor. (180 times 1.22), which is 220 grams of glucose. That's a lot. It's over 50, no, not quite 50%. Okay? I can see head spinning. But that's the amount of glucose you would have to add to 500 grams of water, which is basically 500 milliliters, to change the vapor pressure from 23.8 to 22.8. Decrease the vapor pressure by 1 torr. That's not much. Okay. How we doing on time? 3:22. Got to 3:50. Okay. Let's see. We might be able to leave early. Start the lab early. I think the rest of these are extra credit type problems. So the other thing that's valuable in looking at the review document is you'll be able to see what useful information is going to be on the exam. Right, that'll show you. Because I still follow that policy. If it's in the review document, it'll be on the exam. So you have this big sheet of things that you need to be able to find out where everything is. And then you always have your periodic table here, so you don't have to squint at this one. Okay? So you got a couple of weeks to review. And you can contact me. Of course, all my Tuesday and Thursday classes will meet next week. Anyway, so I'll definitely be here then. And I plan on being here for Labor Day holiday. Because that's what it means, right? Labor Day holiday is supposed to labor, so I'm going to be here laboring. Okay, let me stop this thing so it can be converting. Unless you have any more, if you have any questions. I don't want to stop this before we get everything on tape.